a pair of examples for that two classification algorithm. So first of all, we will talk about a naive-based classifier, and then we will talk about k nearest neighbor. Okay. So what we know about naive-based classifier is that naive-based classification algorithm is a probabilistic classifier. Okay. So is it exploit the properties of base classifier. It is based on the probability models that incorporate strong independence assumption. The independence assumptions do not have an impact on real data. Therefore, they are considered as naive. Okay. So we can derive probability models by using a Bayes theorem. So we can use the Bayes theorem to derive the probability models for naive Bayes classifier. And depending on the nature of the probability model, we can train the naive Bayes algorithm in a supervised learning setting. That means naive Bayes classifier is a supervised learning learning algorithm. So this naive Bayes classifier algorithm needs the data with class information or class level. So naive Bayes algorithm is called naive because it assumes that each input variable or the input features is independent. Okay, that means the input features we are considering are conditionally independent to each other. This is a strong assumption and unrealistic for real data. So if we consider the real data, so this assumption does not make any sense. However, the technique is very effective on a very large range of complex problems. Okay. The naive Bayes classifier approximate the optimal Bayes classifier by looking at the empirical distribution. So empirical distribution means the distribution of the data that we have obtained from experiment and observation. So that is called the empirical distribution. And by assuming independence of predictors, so the naive Bayes classifier is not itself optimal, but it approximates the optimal solution. So first we get the so first we make some assumptions about the input data or input variable or input features, and then we exploit the optimal Bayes classifier for getting the probability in a Bayes classifier. So basically it approximates the optimal solution that we have obtained by Bayes classifier. Now, naive Bayes classifier is a likelihood method which is based on the assumption that the features or the coordinates of X are all independent. Okay. So how do we find independent? Let us consider that if we consider an example of receiving emails to our email IDs, then we can see there are two types of emails. One is so one class belong to non-spam category, another class of mails belong to spam category. Now, if we assume that the words which are found in the emails are conditionally independent, provided that the emails are found to be known as spam or non-spam. Okay, but this assumption is not correct, or this assumption violates the real consideration on the data. Okay. However, if we apply this classifier for classifying the spam and non-spam emails, then this naive Bayes classifier will work fine. Okay. So our assumptions for features are conditionally independent, but if we apply this assumption on the real data, so this will not sometimes this will not be found valid. However, this classifier will work fine. So uh, become conditionally independent means that the likelihood function for each class can be expressed as a product of a marginal likelihoods. So if we consider points or a vector x in which we are having m number of features. Okay, that means this is the m dimensional features. Now for m dimensional features, if we try to estimate the likelihood function probability of x given y equals to c. So here small c is a small c denotes a particular class. Okay, now for this class we have to estimate the likelihood function, and this likelihood function can be expressed as the product of a marginal likelihoods. That means we will get the marginal likelihood for each and every point from x1 to xm, and then we will get the product of those m marginal likelihoods, and this will give us the likelihood function probability of x given y equals to c. Okay, so this is the uh, this is the equation for that likelihood function for naive Bayes classifier, where we get the product of m marginal likelihoods. Okay, so this probability of x given y equals to c will give us the product of this probability of xj given y equals to c. So xj varies from 1 to m, since we are having m number of features and we are having m dimensional feature vector. So therefore, for m dimensional feature vector, we estimate this likelihood function for naive Bayes classifier. The naive Bayes classifier is trained by estimating the one-dimensional coordinate density. One-dimensional coordinate density for each class. Okay, and feature I. So in some way. So in some way means any of the ways above that. So we can get the marginal likelihoods, or but if we look at the Bayes classifier, then we can see that it is uh, it is very easy to estimate the prior probability, but it is not easy to estimate the likelihood in Bayes classifier. But somehow if we can estimate the marginal likelihood for m number of points for each class, and then we can plug this estimation into this equation and get the product. Okay, get the product of m marginal likelihoods for m number of features. Now here in this diagram, we can see that the naive Bayes density estimate for naive Bayes density estimation is done for 3 classes, and this is the prediction that we have made. Okay, so in the last class we have considered a data set of 3 classes. So if we consider the same data set for density estimation, so here we get the naive Bayes density estimation for these 3 classes, and here naive Bayes predictions. Okay, so this white color boundary represent the boundary between these 3 different classes. Now how do we consider that conditionally independent features? So as we have assumed that the features or input variables are found to be conditionally independent, so therefore we can get more elaboration on that. Here let us consider there are t number of classes C1 to Ct, okay, and n observations x1 to xn. Now we need to find the class Ck. So if we consider a particular class Ck, for which probability of Ck given x1, x2 up to xn is maximum over k. Okay, maximum over k. That means we want to get the probability for class Ck maximum over k. Okay, so using the definition of conditional probability, so now we can write that this this probability is given by, that means this is the conditional probability, and this conditional probability is given by this probability, marginal probability. So here we will get the individual marginal probability for t number of classes. Okay, for t number of classes. So considering ck, since here we are getting the marginal probability for a particular class ck, so here we are not getting that here we are considering a particular class ck, so therefore for the ck class we can get the marginal probability for n number of observations or for n number of features. Okay, and independently that we will estimate this marginal probability and get the product of m marginal probabilities in this elaboration. So here we get the, so this is the probability that we want to estimate, and here the naive conditional independence assumptions come into play. So here we assume that all features in X are mutually independent. So conditional on the category CK. So under this assumption, so we can write probability of xi given xi plus 1 to xn, okay, comma ck. So this is given by probability of xi given ck. So this will give us the marginal probability, okay, this xi. So I varies from 1 to n. Under the above independence assumption, the conditional distribution over the class variable c can be given by this equation. So we can write now p of ck given x1 to xn equals to 1 upon z probability of ck. This probability of ck gives us the prior probability, okay, which is multiplied with the product over probability of xi given ck. Okay, so the conditional distribution over the class C we can get from this equation, and here 1 by z is nothing but the normalized factor. So this is used to normalize the conditional distribution that we are getting for class variable C. So let us consider the illustration. Here we estimate the probability of x alpha given y. So here x alpha given y. So here alpha varies from 1 to, let's say 1 to n. Okay, and here x represent a feature point. So from two-dimensional feature point, if we consider two-dimensional data, then this is the original distribution of the data, y equals to 1, y equals to 2. So here y represent the class information. So here we are having two different classes and the corresponding distribution of the data. Here we estimate the first dimension. Okay, here we estimate the first dimension, and then we estimate the second dimension. Now, if we get the data distribution, resultant data distribution for uh, uh, for for this two-dimensional data, okay, or if we consider two-dimensional or three-dimensional or n-dimensional data, then this will be the resulting data distribution. And here we estimate the probability of x alpha given y independently in each dimension. So if we consider the first dimension, so in the first dimension we will estimate the probability independently. Okay, so since there are two different classes, so for the first for class y equals to 1, we get the probability of x alpha given y independently, as well as you will get the estimate probability of x alpha given y. So here probability of x1 given y equals to 2 independently. So for each dimension, we will get the estimate probability of x alpha given y independently. So in the first dimension, here we are considering first dimension and second dimension. So we are estimating the probability in the first dimension, estimating the probability in the second dimension independently. and then we obtain an estimate of the full data distribution by assuming conditional independence. Okay, and after having the independent estimation for each class, and then we will obtain an estimate of the full data distribution by assuming conditional independence. Okay, now take an example, and here we are having four attributes. Four attributes mean four dimensional data. There are four features. Okay, this is one feature, this is first feature, this is second, this is third, and this is fourth, and this is the class information that we have. So here we are having two different classes, mammals class and non-mammals class. Okay, now there is a query is that if say here we have to predict whether the whether this query correspond to a mammals or non-mammals. Okay, so this is the query that has been given to us. So the first for the first attribute, the value is yes. For the second attribute, can fly, the value is no. For the third attribute, the value is yes. For the fourth attribute, the value is no. Okay, now here we have to predict the class. Okay, we have to predict the class. So this is the given data set. We have been given this data set where we are having four attributes and also having the class information. Okay, so let us consider the probability estimation for the different attributes, and then we will get so this will so this independent estimation will give us the marginal probabilities. Okay, marginal estimations. So how to get the marginal estimations? Now let us first consider the mammal class. Okay, for this mammal class, so this is the query. So for the first attribute, the value is found to be yes. Okay, now we will see how many yes are found for this attribute while considering the mammal class. Okay, so in this way we can get 6 by 7. That means there are 7 mammal classes and rest of the 7 mammals. Okay, and rest of the elements are non mammals. Since there are 7 out of 7, how many mammals can give birth? So here there are 6, so we can write 6 by 7. Now out of 7 mammals, how many mammals can fly? Okay, how many mammals cannot fly? Because here the query, the can fly have the value no. Okay, so therefore what we will have to estimate? So the marginal estimation becomes how many mammals out of 7 cannot fly. Okay, so in this way we can get 6 by 7. That means there are 6 mammals who cannot fly out of 7. Okay, and live in water, so how many mammals can live in water, or how many mammals live in water? Okay, now out of 7 we can see two such mammals are found who can live in water, and out of 7 how many mammals have no legs? So we can see from this data set that there are two such mammals who have no legs. So therefore we can get the individual marginal estimation independently, and then we get the product of these marginal estimations. Okay, and this will give us the probability of attribute given mammals, and here we are getting the probability. Okay, similarly we can get for non-mammals. Okay, for non-mammals n, so which will give us this value 0.0042, and for mammal class we got 0.06. Now we will take the multiplication we will take the multiplication of this estimation. Okay, this is called the marginal estimation. Okay, so this marginal estimation can be obtained by getting the product of marginal estimation independently on each feature. Okay, on each attribute. And here we get the multiplication between this probability, and this is the marginal probability of m. So probability of m means how many total, how many in if we consider the number of mammals, then there are 20 mammals, or there are 20 classes. So here we will get the 20. Out of 20, how many mammals are found? 7 mammals. So therefore this probability, this marginal estimation, which will be multiplied by this marginal probability 7 by 20, and here we get for the mammal class, and for non mammal class we are getting this. Now we will compare this outcome with this outcome, and this outcome for mammal class is found to be greater than the outcome for non-mammal class. So therefore, uh, if we uh, if we consider this query for getting the prediction for mammal or non-mammal class, then definitely this will give us the outcome as mammal. So therefore, if some mammals having this property, then from this data set we can predict the corresponding class is mammal class. Okay, so in this way we can apply the naive based classifier, and we can get the prediction for the prospective class. Now this is another example from a naive based classifier. So here we are also having four attributes: chills, runny nose, head assay, fever. Now we have to estimate whether the person is having flu or not. Okay, if this is the query, this is the query, and this in this query we are having four different conditions for different attributes. Okay, now we have to predict whether the person is having flu or not. Okay, so from this given data set, we will get the we will get the marginal probabilities, and then we will get the uh, marginal probability estimation, and from that we have to determine whether the person is having flu or not. So there are two classes, either yes or no. If flu is to be detected as a class level, prospective class level, then we will say the person is having flu, and for that we will write yes. Otherwise, if the person is not having flu, then for that we will have the prospective class as no. Okay, let us move on to another classification algorithm, which is known as k nearest neighbor. Okay, now k nearest neighbor, let us look at some salient features of k nearest neighbor. So k nearest neighbors algorithm, also known as KNN, is a non-parametric supervised learning classifier. So it uses to make classification or predictions about the grouping of an individual data point. Now, while it can be used for either regression or classification problems, it is typically used as a classification algorithm that we know from the supervised learning techniques, considering the assumption that similar points can be found near one another. Okay. Now, for classification problems, a class level is assigned on the basis of a majority vote. That is the level that is most frequently represented around a given data points. Okay. Now a query point is given within the data cloud. Then the points which will be found around the query data points. So we will estimate the majority vote, and from that majority vote we can get the class information for the query data point. Now, while this is technically considered plurality voting, the term majority vote is more commonly used in literature. So here the distinction between these terminologies is that the majority vote technically requires a majority of greater than 50%, which primarily works when there are only two categories. Now, if we consider two classification problem, then this majority voting infers that the majority should be there greater than 50%. Okay. And when we have multi-class, when we consider multi-class problem, so in the multi-class problem, we have more than two classes. Okay. Now, when we have multiple classes, let's say for four classes, so we don't necessarily need 50% of the vote to make the conclusion about a class. Now, here we have to consider the majority voting. Majority vote should be greater than 25%. Okay, rather than 50%. So 50% is considered for two class information, and 25% is considered for four class classification. Now, if we consider eight class classification problem, then how many? So what will be the percentage? 12.5. That means the majority vote that we will estimate or that we will determine should be more than 12.5%. That is for eight different class levels. Okay. Now let us look at this illustration. So here we are having two class. Okay, class A and class B. So here class A, the data points of the class belong to class A are marked in blue color, and data points belong to class B are marked in green color. Okay. Now here we have been provided a query point. So query point is marked in question mark. Okay. So this is the query point. Now you have to determine the class level of this query point. So query point either this query point belong to class A or class B. Okay. Now what we will do, we have to estimate the proximity. Okay, that means how many points are found around this point. So that will give us the proximity, and after having the proximity, we will get the majority of the points which are found close to this query point, and based on that we will assign the class level to this query point. Okay. Now here we get the proximity. So from this illustration, we can say that the query point should belong to class B, because there are since this circle represent the proximity for this query point, and in this proximity we are having two green points and one blue points. Okay, so therefore we can say that this query point should belong to class B. Okay, or class level B. So this is the basic idea behind k nearest neighbor. So first of all, we need to get the point in the point clouds, okay, of m dimensional data, and then we get the then we define the proximity, and in that proximity we get some points which are found to be very close to that query point. Okay, and based on the proximity, we can determine what will be the class level of that query point. Now, regression problems that we use a similar concept as classification problem, but in this case, the average, the k nearest neighbor is taken to make a prediction about a classification. Now, the main distinction here is that the classification used for discrete values, whereas regression is used with continuous ones. So we know that when we talked about linear regression and logistic regression. However, since we need to introduce this classification technique, therefore we need to recall these features about k nearest neighbor. Before a classification is made, the distance must be defined. Since here in k nearest neighbor, we have to get the proximity about the query point. Okay. Now around that point, when we get the proximity, and to get the proximity, we have to get the distance between query points and the points which have been found surrounded the query points, or the points which have been found close to the query point. Now we can use Euclidean distance. Apart from Euclidean distance, we can have many other distance metrics that we also can use. Now it is note that the KNN algorithm is also part of a family of lazy learning models. Now what is lazy learning models? So it means that it only stores a training data set, but it is not undergoing any training stage. Okay. Now the another interpretation about lazy learning of k nearest neighbor is that all the computation occurs when a classification or prediction is being made. So when we make the classification or prediction using k nearest neighbor, then only we get all computations done. Otherwise, what KNN algorithm does, that KNN algorithm only stores the training data set, but the computation is not done. So when the computation is done, when we have to classify or predict some unknown sample using k-nearest neighbor, then only the computation occurs. Otherwise, we only stores the training data set. Now, if we look at some prominent applications of k-nearest neighbor, then we can see that it can be used in recommendation systems. It can be used in pattern recognition. It can be used data mining, financial market predictions, intrusion detection, and many other problems that are used k-nearest neighbor. Okay, k-nearest neighbor becomes increasingly inefficient, and it compromising overall model performance when dataset grows. That means if for a large dataset, the k nearest neighbor algorithm degrades. Okay, degrades. So in that case, we get underfitting problem. হ্যালো, হ্যাঁ আমি আজকে বাড়ি থেকে ক্লাস নিচ্ছি, তো আমার অনলাইন ক্লাস চলছে এখন, ঠিক আছে? হ্যাঁ, কালকে সকালে 11:30টার পর। আমার হচ্ছে সিএসি ব্লক ফার্স্ট ফ্লোরে। সিএসি ব্লক ফার্স্ট ফ্লোর। হ্যাঁ হ্যাঁ, ঠিক আছে। So when the data set grows, the KNNs become increasingly inefficient, and the performance get degraded. Okay, so that means we will when we will have the complex data set of large number of samples, then we will get the underfitting problem, and because k nearest neighbor is found to be very simple classification technique, but it does not work when the data set size grows. So we will talk about this underfitting and overfitting problem later, but for understanding the k nearest neighbor performance, we need. Hello. So these are the different applications of k nearest neighbor algorithm. Now we will compute the k nearest neighbor using distance matrix. Now the goal of the k nearest neighbor algorithm is to identify the nearest neighbors of a given query point, and so that we can assign a class level to that point. Okay. So we have been let us consider that we have been given a query point, and given that query point, we have to identify the nearest neighbor. That means who will be the nearest neighbors among a set of points. So that to be decided using k nearest neighbor algorithm. And for that, we need to take help of the distance matrix, because we need to get the distance between query points and the points which will surround that query point. Okay. Now, in order to determine which data points are closest to a given query points, the distance between the query point and the other data points need to be calculated. Okay, and this distance matrix will help us to form the decision boundaries. Now, these decision boundaries, partition query points into different regions. So if we see the query points, then there will be a bound there will be a partitions are done using these decision boundaries. And we can commonly see the decision boundaries, which can be visualized with Voronoi diagram. So this diagram is known as the Voronoi diagram. In this Voronoi diagram, we can see the different query points are being partitioned, and these partitions are done using decision boundaries. And these decision boundaries are obtained using the distance matrix. Okay, so we can apply the different distance matrix to get these boundaries, and this boundary will give us the partitions over the query points. And this diagram will lead us to give a Voronoi diagram. Okay, this is called the Voronoi diagram. You can remember this name of the diagram, Voronoi diagram. Now, when we apply the Euclidean distance, so in Euclidean distance is the most commonly used distance measure, and it is limited to the real valued vector. Now, using this Euclidean distance, we can measure the straight line between query point and other point that has been considered. Okay. Now, the so some if we consider a query point, so around that query point we will get the points within the proximity. Okay, now those points will be now the straight lines will be determined from the query point to those points. Okay, and this straight line will be measured, and we will determine. And for this, we can use this simple formula of Euclidean distance. Now, there is a drawback of Euclidean distance. So what is the drawback? Now, if two data vectors have no attribute in common, okay? So if we see the attribute values in two different data vectors, and if they are not found to be common, then they may have a smaller distance than the other pair of data vectors containing the same attribute values, okay? So this is the major drawback of the Euclidean distance. However, we can use this Euclidean distance for a single attribute, okay? For a single attribute. So if we want to avoid or get rid of the disadvantage of Euclidean distance, then we can use Manhattan distance. Okay, this Manhattan distance we get p equals to 1. Now what is p? What is p equals to 1? So here we get the p equals to 2 in case of Euclidean distance, but here we get p equals to 1. Okay, so here we measure the absolute value between 2 points. Now, if we consider 2 points and we have to measure the distance between the 2 points, so we will measure the distance, and so here we consider the absolute value of that distance that we measure using Manhattan distance. Okay, it is also referred to as the taxi cab distance or city block distance. taxi cab. It is also called the taxi cab distance or city block distance because it is commonly visualized with a grid. Okay, and it illustrate how one navigate from one address to another via city streets. Okay, so that is why this is called the city block distance or taxi cab distance, because we can visualize this Manhattan distance with a grid. Okay, now there is a drawback of Manhattan distance. Although Manhattan distance seems to work okay for high dimensional data, it is a measure that is somewhat less intuitive than Euclidean distance, especially when using a high dimensional data. Okay, so this is the drawback of Manhattan distance. However, this Manhattan distance is found to be better than the Euclidean distance and other distance metrics, because here we take the absolute value between any 2 points. The next distance matrix is Minkowski distance. This distance measure is the generalized form of Euclidean and Manhattan distance matrix. Here the parameter p in this formula allowing for the creation of other distance matrix. So here how we consider this parameter p here. So here we are taking the 1 upon p. Okay, 1 upon p, and this will define this distance matrix as the generalized form of Euclidean and Manhattan distance matrix. So Euclidean distance matrix is represented by this formula when p is equal to 2, and Manhattan distance is denoted with p equals to 1. Okay, so we will get the same effect of Euclidean distance and Manhattan distance when we change the value of the parameter p in Minkowski distance. The next distance matrix is the Hamming distance. So in this distance matrix, we use the Boolean or string vectors, and here we try to identify the points where the vectors do not match. Now if we consider two identical if we consider two vectors of identical dimension, then we are trying to find the points where the vectors do not match. Okay, so here the pointwise comparison is done, and then we get the points where the vectors do not match. As a result, it has only been referred to as the overlap matrix. Okay, this can be represented with this formulation. Here we can get the summation over the absolute difference between xi and yi. Okay, so here x equals to when x equals to here we get when d equals to 0. That means here we can see that x equals to y. That means x equals to y, we will get a d equals to 0. When x not equals to y, we will get d not equals to 1. Now what are the drawbacks of this distance matrix? The Hamming distance is found to be difficult to use when two vectors are not equal length. So this is one of the major problems with Hamming distance. So we cannot apply this Hamming distance on two different vectors of unequal dimensions. Okay, so when we apply this Hamming distance, we have to get the vectors in identical dimension. Then only we can apply this distance matrix. Otherwise, we cannot apply. Hamming distance code algorithm can solve only single bit issues. Okay, but not the multiple bit issues. So then this is another drawback of Hamming distance. Now here the k value in the k nearest neighbor algorithm defines how many neighbors will be checked to determine the classification of a specific query point. Okay, so when you get the query point, we will see how many neighbors are found in the proximity, and that will determine the classification of the query point. Okay, now for example, if k equals to 1, that means the instance will be assigned to the same class as it is single nearest neighbor. Okay, so k means k equals to 1 means that means there is only one nearest neighbor is found close to the query point. Okay, and the class information that reflect by that nearest neighbor will be the same level for the query point. Now defining k can be a balancing act, as different values can lead to overfitting and underfitting. Okay, so if we get the different value for k, so based on the different values of k, so we will get the different effect means we can get the overfitting problem or underfitting problem. That means if the k nearest neighbor model is found to be very simple but the data set is complex, then we will get the underfitting problem. In that case the bias will be more. Okay, or if we get the model, if we get the k value is found to be more. Okay, k value is found to be uh, k value is found to be more, then we will get, for larger values of k, we will get the high bias and lower variance. Okay, the choice of k will depend on the input data, as data with more outliers or noise will likely perform better with higher values of k. Okay, so we have to choose the k value carefully, so that it will not create any problem like overfitting or underfitting. But we have to balance the k value, so that the overfitting or underfitting problem, whatever the problem is arising, should be minimized. Okay, so we will get the minimal effect of these two issues. Now, what are the advantages of k nearest neighbor? Now it is easy to implement. This is the first advantage. Now, given the algorithm's simplicity and accuracy, it is one of the first classifiers that a new or a new so here we can say the new person who are interested to have in machine learning algorithms, so they can learn easily. Okay, now as a new training samples are added, the algorithm can adjust the account for any new data, since all the training data are stored in memory. Since as we have discussed that using this k nearest neighbor algorithm only stores the training data. So when new data comes for the training, okay, now we get the new data in the training data set, and that must be stored in the memory. So when we predict or classify a new sample or query sample, then only we do the computation. Otherwise we will get all the new data in the training data set, and that has been stored in the memory. Now KNN only requires a k value and a distance matrix. So these two are the only two uh, parameters. So here it is found to be low when compared to other machine learning algorithms. Okay, because here we are only two parameters, k value and distance matrix. So this two information is found to be very low compared to other classification techniques. Now, what are the disadvantages? Now, it does not scale well. Since KNN is a lazy algorithm, it takes up more memory and data storage compared to other classifiers. Okay. So as we have discussed this issue, the curse of dimensionality, the KNN algorithm KNN algorithm is having the curse of dimensionality. That means it does not perform well with high dimensional data points. So as we have discussed that when we get large number of samples in the data set, then KNN lead to the underfitting problem. Okay. Now it is also prone to be overfitting, and due to the curse of dimensionality, KNN also more prone to the overfitting. So reverse the opposite. If we when we get the underfitting problem, so opposite can also be true. We can get the overfitting problem when we get the model is when the model is found to be complex, but the data set is found to be simple, then we get the overfitting problem. So both are true for k and n. So we have to choose the k value carefully so that we can get rid of these issues, or we can minimize the overfitting or underfitting problem. Now let us take an example here, and here we have been given a data set where we have two attributes, age and loan. Okay, so here we have, in the first column we can see the name of the customers. In the second column we can see the ages have been given for the corresponding customers, and this is the loan amount that has been taken by individual customers. And here we have two different classes. Okay, here we need to predict whether the anti default default status uh, is provided by using Euclidean distance or not. Okay, so here we need to predict the default class, whether the default class may be yes or no. Okay, so this is a question mark that we have been put in the row of this tabular data. So here for Andrew, we have to estimate whether the default value is found to be yes or no. Okay, using KNN. So since here we are having two-dimensional data, so age can be represented along y-axis, and along y-axis, or loan can be represented along x-axis. Okay, and then we will get these query points into in this data clouds of different customers. Okay, and then we will get the proximity using some distance metrics, and finally we can predict the class of this corresponding customer in so it may be yes or it may be no. Okay, so this is very easy to predict the class level or class information. So you can take this example as assignment so that you can solve this problem and submit the assignment online. Okay, so you can take this problem as an assignment, and then after solving you can submit online. Okay, that's all for today. If you have any questions, you can ask me. Otherwise, we will start a new topic in the next class.